The reason why I did this whole thing in the first place, as somebody asked, was that when I was a kid, many decades ago, I heard this VLF station and they sent me a QSL card on request, and I set up to visit it, and then COVID happened, and then I set up to visit it again this past summer, and they were supposed to do a transmission. They didn't actually do a transmission because they had an antenna problem. And how weird that is, I'll explain in a short bit. So during World War I, Sweden was neutral. And they had a lot of trouble because all their communications was pretty much running through England. And England was one of the combatants. And the cables were often being attacked by the Germans. And they had a lot of communications to the U.S. because so many Swedes had moved to the U.S. in the late 19th century. Some vast chunk of Sweden moved to Wisconsin and the Midwest. So they wanted a direct communication path that could not be affected by political circumstances, and the direct cable to the U.S. is expensive, but radio is the new and coming thing, so it seemed like a cheap alternative. There was a guy named Ernst Alexanderson who invented the Alexanderson Alternator that we'll talk about in a minute in 1904, and he worked with General Electric in Schenectady to build these things. And in 1919, the GE patents and Alexanderson himself got transferred over to this brand new Radio Corporation of America, RCA, and they won the contract from the government for the link to America. And so they built a transmitting station at Grimeton on the west coast of Sweden, and they built a receiving station nearby at Kungsbacka, and they were both linked to the telegraph office at Gothenburg, which was many miles away. The Grimeton transmitter could directly be keyed by relay from the Gothenburg station. When something was received, it was heard at the Gothenburg station. So the station most of the time was operated completely remotely. These stations communicated with GE stations that were in New York. The receive station was at Riverhead on Long Island, and they had this 9-mile long, what they called a beverage antenna, but it wasn't really a beverage antenna by the way we think about it today, because it was shorter than a wavelength. And the return link from Rocky Point, New York, was on a slightly different frequency, so the link was full duplex.
Scott, I have to ask, you said it was a 9-mile antenna?
Yes.
And it wasn't a wavelength?
Yes.
What
Here's
frequency were they transmitting at?
Here's where it gets good. Just a second here. And this is the basic situation by the 1950s. So they've got this link to New York from Varberg. They've got a link back from New York to Kungsbacka. And then they've got all these other HF links. Those HF links are all relatively recent and relatively low traffic. Up there they've got links to Warsaw, Riga, and Reval. Reval was actually, I think, what's now Tallinn. From Varberg, they've got 2 pairs going to Kungsbacka, the receive station, and then they've got 9 pairs going to Gothenburg Radio Central, which is where the Guy Keen would be, and 4 pairs going to the headquarters up at Carlsberg, and then looks like only 1 from Stockholm to Carlsberg. Not a lot of pairs. The transmitter itself is on 17.2 kilohertz, which you can hear. The return link is coming back at 18.2 or 18.8 kilohertz. Full duplex link, both can key in at the same time. The Grimeton transmitter is a genuine continuous wave source. It's not like an ARC transmitter or something that just you take noise and you filter it down. It produces a clean sine wave that's a pure note in the headphones. And it's not like the Marconi system. For a while, it wasn't allowed to talk to Marconi operators because it wasn't licensed with the Marconi patents. Because of the size of the alternator and the size of the antenna at these low frequencies, the GE system was not very well suited to put on board a ship. But it's got some big advantages for transatlantic links. Here's the demo. You can see all the way to our left is this huge alternator and racks of control logic on the right, and the man operating the key in the middle. There is local control today since the remote control no longer exists, since the telegraph system no longer really exists. From the power line to the antenna, here's how it goes. AC power comes in from a power station. Not necessarily the most reliable grid power in 1919. Today, it's coming off of the normal 50 hertz grid. Some of that power is going into motor generator sets that produce operating DC power. One of these generators provides 125 volt for lamps and relays. One of them provides 250 volts to excite the alternator field coil, and for powering the transductors for keying. And I'll explain the transductors in a little bit because that's another very cool piece of EMAG stuff. There's also a 500 volt MG set that supplies higher voltages needed for the automatic speed control, and the field coils for that are powered off of the 250 volt generator. No rectifier, well, they in fact call these rectifiers, but no diodes, not even rotating contact stuff, just AC motor, DC generator. To the far right, you can see blowers, which are providing air to cool and blow out the arcs on the high power contactors. All this stuff is very big and very high power. It's incredibly steampunk.
It's like a wind tunnel drive.
It does. It looks a lot like a wind tunnel drive in a lot of ways. Big two-phase induction motor running below synchronous speed, just like a wind tunnel. And it's a two-phase induction motor, so it's two phases 90 degrees apart, running off a Scott T transformer, which turns the three-phase power into two 90-degree phases. And that seems a little unusual, but first thing is that was kind of standard back at that time. And it also allows the motor to run at very high slip, which allows you to get considerable speed control. Not the wide range of speeds that you want for a wind tunnel, which is why the control is a little bit different. Alternator, step up, gearbox, fixed ratio into the alternator, the RF alternator. And I know it's hard to think of 17.2 kilohertz as RF. That's baseband audio in my world. I can just barely hear it. Little kids apparently can hear it very well and aren't happy. You can, in fact, throw a wire out and attach it to a sound card and pull data. Yeah, here's another view of the alternator going into the gearbox. This smaller motor up here is just providing oil pump, because all of this has plain bearings in it. So it's got to have all the bearings up to oil pressure before the thing starts rotating.
So they're true batted bearings. They're not roller bearings or needles or anything.
Right, right. No balls. It's
Just like a ship.
once the speed is roughed in, and they're roughing in the speed by bringing the thing up and then looking at the operating frequency, they have an automated speed control. It's a closed loop control. There's a pulse generator. One of the coils on that big alternator produces periodic pulses, and that goes into an integrator, and that drives a magnetic amplifier, which they refer to as a transductor, which adjusts the voltage on the field coil along with the motor speed. This was called Tyrrell regulation, and it apparently was common at the time. But it's a closed loop system, and once it's on frequency, it locks there and it stays there. And this was all done before Black's analysis of the feedback control systems. So all of this was built entirely empirically. The magnetic amplifier is a saturable reactor. It's a choke, and it blocks AC because it's a big choke with a high inductance. And then it's got a second winding, and when you put DC on that second winding, the choke saturates and AC starts flowing past. So with a small DC current, you can control a huge AC current. Since this amplifier is controlling the motor itself, it's operating at 50 hertz, and so it's very large because you need a very high inductance in order to block 50 hertz. But we'll see a smaller version of this used elsewhere here. This was apparently one of Alexanderson's other inventions, and he was very proud of it and used it everywhere he possibly could. In order to actually do the rough control of slip on that induction motor, they had big tanks of fluid, and it was a baking soda solution, and they just run the electrodes up and down. Same thing they have in the unitary tunnel. And when I saw that, I said, "Oh, I see that all the time."
Same thing you use in a blast furnace also. The electrical blast.
That would make sense. It's an easy, continuously adjustable resistance. Being very careful about how much bicarbonate was in the system, because too much and you have corrosion issues, and too little and you don't have your resistance in the right range. You know, if you're used to looking at wind tunnels, this is a whole lot smaller. Induction motor, gearbox, alternator. Induction motor is running at 711 RPM. Gearbox is a ratio of about 1 to 3, a little bit lower than that. Alternator itself is running at about 211 RPM. 488 cutouts in the disc that's rotating, and so total of 17.2 kilohertz. The alternator is not really like a conventional AC generator. There's a notch disc and it's spinning past DC coils and pickup coils. And so the reluctance in that gap is changing and pulses are getting induced in the pickup coils. It's more like a guitar pickup than a conventional generator. And because of that, the output power is mostly a function of the DC input power and not the mechanical power on the motor. So the motor load varies a little bit with modulation. You put the key down and it slows a little bit, but not very much. The stability is very good. And so that's why this arrangement is used instead of just a direct high-frequency generator with a bunch of coils. There's a little bit of change in load, and so there's a control signal that goes directly to the transductors when the key is down to speed the thing up a little bit. That eliminates whatever residual chirp there is. Each of these windings are producing 100 volts at 20 amps or so. So you've got 20 kilowatts of power coming out of the alternator. And most of that 20 kilowatts is from DC going into it, but a lot of it is still from that AC running that induction motor. They didn't normally run 200 kilowatts. They normally ran just enough power to get good copy, which was usually around 80 kilowatts or so. Speed of the induction motor has to be 711 RPM in order to get the correct frequency out of the alternator. It's set roughly with a tachometer, and then somebody sits there with a stopwatch and a Vita root counter on the gearbox. 3 seconds with the stopwatch, the counter reads 2134 rotations. And today they use a Hewlett-Packard counter. The alternator is pretty much immune to load. The antenna is a relatively high impedance load, so keying is not a big deal. The output of the alternator goes into a matching transformer and out to the antenna. The secondary of that transformer is shorted by another magnetic amplifier. So with the key down, DC power goes to the mag amp, which causes it to short out the antenna circuit, and the antenna radiates. When the key is up, there's more capacitance in the circuit, and it gets detuned. So with this method, the transmitter still leaks about 10 dB of signal when the key's up. And this is critical because the receiving station is not that far away and is very sensitive. And that's why it had to be as far away as it is. The transmitter is impedance limited by its nature, so it can transmit into a short or an open without any problem. But the change in load causes a change in load on the power line. Power grid takes up the slack, not the transmitter itself. In this picture, you've got the matching and keying hardware. 2 of the 4 motor controlled transductors are at the bottom. And on the right and left-hand sides, there are all of these modern transmitters that were used in the 60s. They're trying not to talk about, although that would be another cool discussion as well. Up at the top there, magnetic amplifier for keying. This is the mag amp that's carrying 17 kilohertz. So RF coming in through that big copper thing, coming out the other end, and then this sort of gray Y thing is the DC power to the DC windings inside there.
So this is a controllable magnetic chip.
Yes, it was actually used in a much smaller form in the V2 rocket for control surface changes. But the Germans by World War II had much better magnetic materials to do it. These are just being done with soft iron.
Yeah.
So the efficiency is not all that great. And the antenna is not perfect. The antenna resonance points change with weather. So there is a variocoupler. You can see there are coils inside and coils outside, and you can twist the two in order to do antenna tuning. These towers without T's on them, again, are modern antennas. There's actually a log periodic down at the end. But these big ones with the T's on top, 6 towers, 127 meters tall, 300 meters apart. So it's about 2.2 kilometers or about 1.4 miles from one end to the other. Each of these have a hammock of 8 wires that are suspended from tower to tower up at the top. And this picture isn't really good enough for you to see that. It's driven on one end with respect to ground through a series loading coil. And then at each one of these 6 towers, there's a vertical wire coming down from the hammock to a loading coil on the ground, and then a grounding system.
Is it loaded from the end or from the middle?
There's a load at the end where the transmitter is,
Okay.
and then each one of the 6 vertical lines has a load on it. This is on the transmitter side. This is the loading coil. The thing is, with that hammock, you've got this parallel capacitance to ground, which is like 0.47 MFD to ground. And that's in parallel with all of these vertical, and the vertical elements are the ones that actually radiate usefully. Loading coil, 4.7 MFD, very, very high Q system. So the resonance is only about 40 hertz wide. And they're fiddling around with that variocoupler to keep the resonance in the right place. Because the resonance is so sharp, the system rings severely, and it can take some milliseconds to get up to full power after signal's applied. And then when you let up the key, it takes a few cycles for the thing to quench down. That, combined with the speed of the contactor relays, limits the maximum to about 100 words a minute. The antenna works by current flowing through a wire, creates a magnetic field in free space, which creates an electrical field in free space, right-hand rule, all that stuff. So current is flowing through the vertical elements, creating a wave moving along the horizon, and the current moving through the horizontal element, that hammock on top, creates a wave that is polarized horizontally instead of polarized vertically. You can model this as just 6 parallel elements, each in series with a loading coil, in parallel with a big shunt capacitor. The wavelength is so long that this is a point source. You can just think of this whole thing as just a lump sum element, and it's more than a mile long. 6 radiating elements, so the load impedance is 1/6 of what a single one would be. So the voltage is reduced by that much. And as it is, the voltage is very high. Ground currents are critical, and they have an elaborate grounding system. And they like to talk about the grounding system because the grounding system is the other half of the antenna. But having multiple elements is the interesting part here. In addition to the radiating elements that are vertical, there are also a bunch of tensioning elements and springs in order to keep the whole thing at the proper tension. If it moves a little bit out of place, well, you can get out of your tuning range real easily because the tuning range is so narrow. And that's what happened, is they just had something that had to be retensioned. This was like a substantial portion of the country's budget. And this is why RCA was so rich. At crazy low frequencies like this, propagation is not by ground wave, it's not by sky wave, it's not line of sight, it's this weird fourth mode. The lowest level of the ionosphere is only a couple wavelengths above the Earth. And we're talking about the A and B layers that HF people never think about because it's below the D layer. Nobody thinks about it.
Never talks about it.
So what you wind up with is a waveguide that's formed between the conductive ocean and the conductive ionosphere. And it just pipes a wave a long distance along the curve of the Earth. But like ground wave, ground conductivity is absolutely critical, which is why the station was built right on the water, and the station in the US was built right on the water, and it propagates really well over the water and then stops pretty abruptly once it gets to New York and into areas where the ground conductivity is a little bit poorer. The wave that comes off of that hammock disappears because it's horizontally polarized. It doesn't propagate. Only the vertical portion actually propagates down through that waveguide. The shorter the wavelength, the more attenuation in this mode, because the waveguide is more wavelengths across, so lower frequencies are more desirable. There were fights among customers of the system for the lowest possible wavelength. SAQ got a really desirable frequency. Most of the theory for the ELF propagation wasn't worked out until the 1950s. So at the time this was built, this was again entirely empirical. Nobody really knew why it was working, but they knew that they had consistent propagation to the US, day or night, didn't change that much. And it didn't change that much with the solar cycle either. But that's basically the look through. Is an incredible amount of effort was put into building this thing. And I feel really bad that I didn't actually see the thing transmitting after going all the way across the Atlantic to see it. But it was a good excuse to eat salty licorice too. I do have pictures of the receiver station. Nobody really knows much about the electronics in the receiver station. There aren't really any records kept of what it was other than that it was tube-based. The receive station does not still exist at all. And none of the stations on the US side still exist. It takes like 3 operators, including the guy who's keen, who's someplace else. And they were running, pretty much 24 hours a day when this thing was new. But they've also got a large maintenance staff. They've got a full machine shop. Because it's not easy to ship stuff from the US, a lot of stuff was having to be fabbed on site if parts were needed. So they had a very elaborate fab facility. Not only is this a lot of money, but the R&D going into it must have been a fabulous amount of money. And a tremendous risk too. People don't want to spend that kind of risk these days.
Well, the US Navy runs that system up in Minnesota at 11 kilohertz?
Somewhere around there. And there's, in Hawaii, there's one in Mapunapuna that is this really long antenna that's like 3 feet off the ground. I saw that when I was a kid and I didn't really get it, but now I get it a little bit better. It's not as long as this is because real estate just isn't available. This is kind of in rural Sweden where real estate is not so much of a problem, and it was probably less of a problem in 1990.